Okay, good afternoon. This file contains the pre-lecture slides for class on Thursday, September 5th, 2013. The relevant reading from the Carey textbook edition 8 includes chapters 2.11 through 2.19. We are also including in this pre-lecture section 4.1, which covers functional groups. For students using a text edition other than 4.1, be sure to locate the book section listing out all of the functional groups that are relevant for this course. Okay, so for today we continue our discussion of hydrocarbon chemistry with particular attention to the IUPAC naming system that the chemistry community uses to name alkanes. Alkanes are the simplest structures we will work with this semester, and the naming system for alkanes forms the basic foundation for the naming of all organic compounds that you will be exposed to both in 232 and 234. Rest assured that if you can name an alkane, it will be trivial later on to name compounds with functional groups added to them. To that point, we use the phrase functional group to refer to any substituents that confer specific chemical and physical properties to a compound. Remember that a substituent is any atom or group other than carbon or hydrogen atoms attached to any hydrocarbon. Functional groups then encompass a variety of atoms and groups, such as alcohols, amines, and carbonyls, all of which we'll talk about towards the end of the pre-lecture. Okay, so we begin by covering the nomenclature for naming unbranched or straight-chain alkanes. The first four alkanes have unsystematic names that must be memorized. These are methane, CH4, ethane, C2H6, propane, C3H8, and butane, C4H10. On this slide, I've included both the condensed formula and the bond line diagrams to help you practice recognizing these symbols for the simple hydrocarbons. Notice that for methane, there is no bond line formula because methane consists of only one carbon atom with 4 hydrogens, so there's nothing to draw a line between. Starting with pentane, C5H12, alkanes have a systematic naming structure based on Latin or Greek prefixes combined with the suffix ane. So here we see pentane, C5H12, which has P-E-N-T, pent, in the prefix. That tells us that there are 5 carbons in this alkane. We know it's an alkane because it has ane in the suffix. Based on the general formula here, we know that pentane must have 12 hydrogens in it since it has no substituents or functional groups attached to it. Moving up in the number of carbons, we can see we have hexane, heptane, octane, nonane, and decane. Again, each prefix tells us the number of carbons that are in the alkane, and we know it's an alkane because the name ends with ane. Once again, we can figure out the number of hydrogens that are attached to the alkanes based on the number of carbons that are in there, ensuring that we always have 4 bonds around each carbon. Note that as presented in a series from CH4 all the way through decane, these compounds represent a homologous series of compounds that follow the same generic formula with increasing values of the subscript n. That is, all alkanes have the generic formula C sub n H sub 2n plus 2. If you see the molecular formula follows this generic formula, you know that you must have an alkane represented. In your textbook and elsewhere outside of the course, you may run across the letter N as a prefix before some IUPAC names. The letter N stands for normal, but it's an archaic way of naming simple unbranched alkanes. This is a type of common name, but it is not an IUPAC name. So for example, the IUPAC name for C4H10 is butane, but if you see N-butane, know that that's the common name. You do not need to put an N before any common name in this course because it's already implied in the IUPAC name. Just use the simple IUPAC name for basic alkanes. Okay, so note that as we learned in week 1, organic chemistry focuses on the relationship between molecular structure and the chemical and physical properties of a substance. Homologous series provide a good example of this relationship for us to see how structure affects physical and chemical properties. Here on this slide, I've included some 3D models of methane, ethane, and propane, as well as their dash wedge formulas for the compounds. Notice that the difference in boiling point between these compounds seems to be in some way related to the molecular weight of the compounds, with methane having the lowest boiling point and propane the highest boiling point. Methane, of course, has the lowest molecular weight, and propane has the highest molecular weight. Consider how the structure of each molecule might affect the boiling point of the respective substances. Remember, in general chemistry, boiling point relates to the strength of the intermolecular forces between compounds. In this case, we have all nonpolar compounds. Note the absence of dipoles. There's no dipoles drawn anywhere on this slide, okay, that are mutually attracted to each other solely by van der Waals forces. As the length of the alkane chain increases, so too does the surface area of the molecule. As such, longer molecules have more surface area that increases the strength of the van der Waals forces between them. The increased van der Waals forces, in turn, hold the molecules together more tightly in each substance, and it therefore takes more energy to separate each molecule from one another into a gas phase. Accordingly, the boiling point is observed to be higher as the molecular weight increases or as the length of the alkane chain increases. In fact, these forces become so great that higher molecular weight compounds have such high boiling points and melting points that at room temperature we can observe them as high viscosity oils and waxes. So to this point, we've just talked about the IUPAC naming systems for small straight chain molecules. You will encounter in this course molecules that are cyclic and not straight chain. The IUPAC naming system for cycloalkanes is a very simple system based on the rules that you just learned for the basic straight chain alkanes. Cycloalkanes are any alkanes that contain a ring of 3 or more carbons. Cycloalkanes must have at least 3 carbons in them to form a ring. Any less than 3 and there aren't enough carbons to make a ring. Okay. To name cycloalkanes, you simply count the number of carbons in the ring, add the prefix cyclo to the IUPAC name of the unbranched alkane that has that same number of carbons. So for example, on the bottom left, we see a ring that has 5 vertices in it. We know that using bond line formulas, each vertex indicates a carbon atom. So the 5 vertices means there are 5 carbons in the ring on the bottom left, compound 1. An unbranched alkane with 5 carbons we would call pentane. Therefore, this cyclic cycloalkane with 5 carbons in it we would call cyclopentane. On the bottom left, compound 2 has 6 vertices in it. 6 vertices indicate that there are 6 carbons in this ring. An unbranched alkane with 6 carbons we would call hexane. Therefore, for this cyclic structure, we would append it with the prefix cyclo and call it cyclohexane. What about branched isomers? Okay, the rules that we've talked about right now cover only straight chain molecules as well as cyclic alkanes. Okay. Here on this slide, we can see a series of structural isomers that all have the exact same molecular formula of C6H14. However, only the first compound bears the name hexane. It is the only compound on this slide that has a single continuous unbranched chain of 6 carbons in it, giving it the name hexane. The other 4 isomers listed on the slide have the exact same number of carbons and the exact same number of hydrogens as the first structure, but they're all spatially arranged as branched structures. A more complex naming system is thus required to account for the differences between isomers and not to confuse them with the straight chain unbranched hexane. Note, we cannot use the name hexane to refer to any of the 4 isomers at the bottom of the slide because it refers exclusively to the straight chain unbranched structure listed at the top. So, to name branched alkanes, our naming rules become a little bit more complicated. Okay? You can name any branched alkane by following 3 simple steps, as listed here on this slide. Okay? First, find the longest continuous chain of carbon atoms and use the IUPAC name of the unbranched alkane that matches that number of carbons as the basis of the name. Okay? Once you have the basis, you add to it the name of a substituent coming off of the basis as a prefix. Okay? You also include a number indicating the location of the substituent on the basis by numbering the chain from the end nearest to the first substituent. Identify the carbon of that substituent and use it as a prefix attached to the substituent name. Okay, remember, a substituent is any group that is substituted on a carbon backbone in place of a hydrogen atom. Okay, so on this slide we can see an example of detecting unbranched alkyl substituents. There are two new symbols included on this slide that you should understand. First, in the upper left, notice the letter R. R is used in your textbook in this course to indicate any alkyl substituent. That's a substituent that includes only carbon and hydrogen atoms. Okay? R indicates that an alkyl substituent is being listed, but it's unknown what it is, and we don't want to write it out. We simply use R to indicate alkyl substituent. Okay? The squiggly line indicated in the upper right indicates a cut point or a place that a substituent, in this case an alkyl substituent, is attached to a backbone. Note the relationship between the RH in the upper left and the R with the squiggle line on the right. What I've done here is remove the hydrogen atom, included the squiggle point to indicate that this R group could now be attached to an unbranched straight chain molecule at that specific cut point. To name an unbranched alkyl substituent, simply take the IUPAC name of the corresponding unbranched alkane, replace the ANE ending of that name with the letters YL, pronounced ill, and you have the name of the alkyl substituent. Remember, R is just an abbreviation for the alkyl group. We'll learn the specific names of the alkyl substituents on the following slides. Here on this slide, we have the two simplest alkyl groups, the methyl and ethyl groups. Notice the similarities between each of these groups and their straight chain unbranched counterparts from which their names are derived. The methyl group, CH3, is similar to a methane group with one hydrogen removed. Thus, it is called methyl because we remove the ANE from methane and replace it with YL. Similarly, at the bottom, the ethyl group looks very similar to the ethane unbranched alkane with one hydrogen removed. The name ethyl, again, is derived from removing the ANE from ethane and replacing it with YL to become ethyl. Let's walk through the butyl substituent to see exactly how we name substituents that contain only carbon and hydrogen atoms, the alkyl substituents. Okay? Remember, if the potential point of attachment as indicated on this slide is at the end, all you do is take the IUPAC name of the corresponding unbranched alkane, take ANE off the end, and replace it with YL, and you get the name of the substituent. So here at the bottom of the slide, I've indicated for you the butane molecule with three different representations. All of them mean exactly the same thing. At the bottom left is the Lewis diagram. At the bottom right, we have both the condensed formula as well as the bond line diagram. This is butane because it has 4 carbons in it, and we've memorized the name of the 4-carbon alkane. Here, all I've done is drawn out one of the hydrogen atoms on the condensed formula as well as on the bond line formula to illustrate the cut points that are going to form. We cut here to remove the hydrogen atoms. Now they're gone. And we replace them with an R group, indicating that the previous butane molecule has lost a hydrogen and is now attached to a longer straight chain structure. Using our IUPAC naming system, we remove ANE, replace it with YL, and we go from butane to the butyl alkyl substituent, indicated in all 3 of the representations. Consider the following 2 substituents and see if you can identify their names on your own before I give the answer. Obviously, you can pause the slideshow, derive the names, come back to it to see the answer, so I'll keep moving. Up at the top, all we need to do is simply count the number of carbons, identify the closest hydrocarbon, alkane, that has the same number of carbons to identify its name. Simply counting from left to right, we see we have 1 carbon plus 4 here, 5 total, plus 1 is 6. There are 6 carbons in it, which means that this substituent is most closely similar to the hexane unbranched alkane. Following our naming system by removing ANE and replacing it with YL, this becomes the hexyl group. Let's do the same thing at the bottom. Count 1 carbon here, plus 7 carbons here, plus 8, plus 1 more, means we have 7 plus 1 plus 1. There are 9 carbons total. The unbranched equivalent, that's most closely similar, would be of 9 carbons, which would be nonane. Remove ANE, replace it with YL, and you get the nonil group. So let's use these rules to step through the names of these two isomers of C6H14 here, two of the branched isomers of hexane. So let's do the top one first. Okay? First, apply rule 1. Find the longest continuous chain and use the IUPAC name of the unbranched alkane as the basis. All right. So starting from the left, we can count to find the longest continuous chain. 1, 2, 3, 4, 5. Okay. Let's start from the top. 1, 2, 3, 4, 5. Well, that's the same length. I see one more way to count. 1, 2, 3. Well, 3 is less than 5, so either of the two 5-length chains would give us our longest continuous unbranched alkane as the basis. 5 carbons corresponds to pentane, okay, which is the basis of the name of this alkane. Okay. So, step 2, add the name of a substituent as a prefix to the basis that we've already decided. Okay. So I'm just going to circle the basis here in this structure so that we can keep track of it. Here it's circled, which means that the cut point is right here. Coming off of this alkane is a CH3 group. Remember, in the bond line diagrams, the end of any line indicates a carbon atom as long as there's no heteroatoms listed there. So that means there's a CH3 group coming off the top. Recall that the name of a CH3 alkyl substituent is methyl. We simply add that as a prefix to the basis. So this is a methylpentane. The final step requires us to number the chain from the end nearest the substituent and identify the carbon to which the substituent is attached by number. Once again, just for convenience, I'm going to circle the basis so we can keep track of it. Okay? And now we're going to number the chain of we're going to number the longest chain from the end nearest the first substituent. Well, the substituent is right here. We'll indicate it with a little squiggle coming off. This substituent is closest to the left side of the molecule, furthest from the right side of the molecule, so we start numbering from the left side. So we'll put a 1 here, a 2 here, a 3 here, a 4 here, and a 5 here. Okay? We append the number, this is called the locant, of the substituent before the name of the substituent in the IUPAC name. So the methyl group is located at position 2, so this molecule gets the name 2-methylpentane. Okay? Easy, right? Let's do one more. Okay, so same 3 rules. Okay? Find the longest continuous carbon chain and use the IUPAC name of the unbranched alkane as the basis. So let's count from all directions. 1, 2, 3, 4. 1, 2, 3, 4, 5. 5 is longer than 4, so we know that the 5-carbon chain is the basis in this structure. If you count from the other side, you'll see it's the same. 1, 2, 3, 4, 5. Okay. 1, 2, 3, 4. Okay. 5-carbon is the longest continuous chain, so again, this is a pentane isomer of hexane. Okay. Step 2, add the name of a substituent as the prefix onto the basis. So once again, let me just circle the basis so we can keep track of it. Okay. And indicate the substituent with a squiggly line, okay, right here. Notice that once again we have a methyl group coming off of this basis. End of a line indicates that there's a C there. Carbon must have 4 bonds, so it's a CH3 at the end of this bond. CH3 corresponds to a methyl group. So this structure also gets methyl before the word pentane. Final step, okay, number the chain from the end nearest the substituent and identify the carbon to which the substituent is attached by its number. Okay, let's circle that basis again just to keep track. Okay. And hopefully you'll notice by now that if we count from either end, the methyl group is an equivalent distance, okay, because it's in the middle of the molecule and the molecule is symmetric. So I'm just going to start numbering from the right side just because it's convenient for me. 1, 2, 3, 4, 5. Okay? In this isomer, the methyl group substituent is attached at position 3, so we append that to the IUPAC name as a prefix, 3-methylpentane. Here are the two isomers side by side, 2-methylpentane and 3-methylpentane. Hopefully you can see as they're side by side why we need to indicate the locant of each substituent in the name. Without the 2 and the 3, we would have no way of distinguishing these two structural isomers from one another based on methylpentane alone, because they would both have the same name. With the locants indicated, 2 and 3, we know that one of these structures has a methyl group at position 2, the other has a methyl group at position 3. Okay. Importantly, note that these are constitutional or structural isomers of hexane, even though pentane is in the name. Okay. Once again, pentane is the basis of both of these structures, but they are isomers of hexane. Okay, so what do we do if we have more than one substituent? Okay. Throughout the semester, you're very likely to encounter many compounds that have more than one substituent on them. To name these compounds, you simply add a prefix to the beginning of the substituent in the name that indicates the number of each substituents that are there. So as we can see here, we use Greek prefixes for this, with di meaning 2, tri meaning 3, and tetra meaning 4. So if you have 2 methyl groups, we say dimethyl. If you have 3 methyl groups, we say trimethyl. If you have 4 methyl groups, we say tetramethyl. We also include the locant number for each substituent that's on the basis. Remember, we have to include it for each and every one so we know where they are and are able to distinguish between isomers that have the same basis in their name. So as you can see here up at the top, we have 2,3-dimethylbutane, okay, with a methyl group located at position 2 and one at position 3. At the bottom, both of the methyl group substituents are located at position 2, so the name is 2,2-dimethylbutane. So, what about alkyl substituents that are attached in the middle of their chains? Okay? For any substituent that is longer than an ethyl group, for example propyl, as I've shown here, it becomes possible to attach the substituent itself at multiple locations. What this means is that each of these substituents themselves can be branched. This will occur when the substituent is attached anywhere else other than the end of the chain. So with the simple propyl group shown here, up at the top we have a cut point at the end of the propyl chain. Okay? Down at the bottom we have a cut point in the middle of the propyl chain. Okay? In effect, this is a straight chain or unbranched alkyl substituent at the top. Down at the bottom we have a branched substituent, also a propyl substituent. Okay? Note that the formula for these alkyl substituents are identical to one another, but they connect in different locant points, so we have to have different names for each one of them in order to distinguish them. So the IUPAC system for naming branched alkane includes the 4 rules that are listed here. Basically, you're creating a unique IUPAC name for the substituent as if it were its own separate base compound. You would then append the name for this substituent to the basis of the parent chain it is attached to. Okay? Fortunately, in this course, we are going to learn the common names for branched alkyl substituents, which are a bit easier to recognize. Although these names do not have any systematic rules behind them, it's simpler to simply memorize them than it is to apply the IUPAC naming system for the entire class of branched alkyl substituents known to us. All students should be familiar with the IUPAC system, but ensure you can recognize the common names for these substituents. So for example, the branched propyl substituent that's listed on this slide with 3 different representations has the IUPAC name 1-methylethyl, but the common name isopropyl. You are responsible for the common name isopropyl of this alkyl substituent. In fact, on this slide I've included the 4 most common branched alkyl substituents that you will see in this course. Starting from the left with our isopropyl group from the previous slide, we see 3 different versions of butyl substituents, including isobutyl, sucbutyl, and tertbutyl. Although there are other branched alkyl substituents that you'll encounter in the book, these 4 are the ones that we will encounter most frequently, so you should learn to recognize them as soon as possible. What do you do if you have substituents on cyclic structures? Well, you do the exact same thing you would do with any branched alkane, simply using the cyclic structure as the basis. There are two examples listed for you here on this slide. Remember, to name the basis of any cycloalkane, you simply count the number of carbons that are in the ring. In this case, we have 6, so we know that this is a cyclohexane. Okay? Identify the substituents coming off of the cyclohexane ring. Up here, we have a methyl group coming off. Down here, a 2-carbon ethyl group. So we append with prefixes the locants and names of the substituents to the basis, making this compound 1-ethyl-3-methyl cyclohexane. In terms of the ordering of the substituents as listed before the basis, we simply put them in alphabetical order since both of them are alkyl substituents that have equivalent weighting. At the bottom, here's another example. Okay. In this case, we have a 1, 2, 3, 4, 5-membered ring. So this is a cyclopentane ring. It has an ethyl group coming off here and 2 methyl groups coming off here, which make it 2-ethyl-1,1-dimethyl cyclopentane. Note that again, ethyl comes before methyl, and we don't include the prefix di before as part of the alphabet naming system. So E comes before M. We exclude the di in ordering. Note that we include 2-ethyl to indicate that this is at position 2, 1-1, again, each locant repeated because both methyl groups are located at the exact same point. Warning, quick warning here. If the cyclic structure contains fewer carbon atoms than the substituent coming off the cyclic structure, the chain becomes the basis and the ring becomes the substituent. So here in this example, we have a 3-membered ring attached to a 5-membered chain. 5 carbons is more than 3 carbons, so the basis here is actually pentane with a 3-membered cyclopropane ring attached. We simply name this 3-cyclopropylpentane using the exact same system of removing A and E, replacing with YL to indicate that a cyclic structure is the substituent coming off of the pentane backbone. So, the introduction that we've had to branched alkanes allows us to address the concept of degree of substitution. Okay? Degree of substitution refers to the number of carbons that are attached to any given carbon in a hydrocarbon. In order, from fewest number of carbons attached to largest number of carbons attached, we have primary, secondary, tertiary, and quaternary carbons. Primary carbons attached to only one other carbon, secondary attached to 2 other carbons, tertiary to 3, and quaternary to 4 other carbons. At the bottom of the slide, I've indicated with color-coded arrows the degree of substitution for each carbon in the 3 substituents you see listed. Okay. Down here in the isobutyl group, the yellow arrows indicate the 2 primary carbon atoms. Right? This methyl group is attached only to 1 carbon. So too this methyl group is attached only to 1 carbon. In green, we see that this CH2 group is attached to this carbon here, as well as the carbon that's in the alkyl group coming off of it, making it secondary. This carbon here in the center is tertiary because it's attached to 1, 2, 3 carbons. So too over here in sec-butyl. Finally, the only quaternary carbon we have is in the tert-butyl group, which is attached to 1, 2, 3, 4 carbons. It'll be important as you move through the semester to quickly identify the degree of substitution on any given carbon atom, as it will be important to the mechanisms we learn later on. So let's do one quick last example here to name this compound. Okay, stepping through our rules, we again identify the longest chain. Hopefully you can see with me that the longest chain in this compound has 1, 2, 3, 4, 5, 6, 7 carbons. No matter how you count this from any end, you'll see that the longest chain has 7 carbons, making this a heptane. For ease of viewing, I will again circle the base here, which allows us to identify 2 substituents coming off the top, both of them methyl groups indicated by the terminal lines. Okay? With 2 methyl groups, it means we have a dimethyl heptane. Okay? But before I add the di, remember I need to indicate the location of each of those methyl groups with a number for its locant. Numbering from left to right, 1, 2, 3, 4, 5, 6, 7. Thus, this compound is 2,6-dimethylheptane. Okay, so with all this talk about naming branched compounds, you may have come to the point of wondering, who cares? Why am I learning how to differentiate the names of branched compounds from their straight-chain isomers? Remember, structure is everything in organic chemistry, as structure directly affects the chemical and physical properties of all compounds. Here you can see the absolute boiling points for butane and its branched isomer isobutane. Notice that isobutane boils at a much lower boiling point than butane does. Consider why this might be the case. Recall how van der Waals forces explain the difference in boiling points between straight-chain compounds in homologous series. The same principle is in effect here. Basically, the unbranched butane molecule is better able to stack neatly with other unbranched butane molecules, which improves the surface area contact and thus contributes to greater intermolecular attractive forces. The boiling point is higher because these molecules stick together fairly well. In contrast, the branched isomer does not stack so easy, resulting in fewer van der Waals contact points and weaker intermolecular forces. In this case, isobutane molecules aren't stuck so readily together, and it's easier for them to separate into vapor phase at much lower temperatures. Practically speaking, we care about the differences in structure in our daily lives as well. For example, the inkjet printers that so many of us have used are built with special inks that contain an alcohol solvent that is an isomer of propanol called isopropanol, indicated with the green check mark at the bottom of the slide. Note that propanol and isopropanol have the same molecular formula, but one compound is branching and the other one is not. Modern inkjet printers use isopropanol because the boiling point is much lower than that of regular propanol. With its lower boiling point, isopropanol-based inks dry much faster than propanol-based inks. Because of this, we can get much cleaner ink prints out with much less run on the page, which makes isopropanol the solvent of choice for most brands of inkjet printer ink. Okay, so lastly, it's important to master the basic nomenclature system covered here in this presentation, because the system will become increasingly complex as we introduce new functional groups over the course of the semester. Each functional group has its own specific name, and we will learn about each one in detail on a weekly basis. However, in anticipation of learning about the functional groups, I've included each of them here on this slide. It's a good idea to commit their names to memory now so you can easily recognize them as we learn how to name them and we learn their reactivity over the course of the semester. On this slide, note that I've drawn in red the specific atoms that are included in the name of the functional group. In black are just alkyl substituents hanging off of the functional groups. Okay. With that, that is all for this pre-lecture. As always, be sure to review the relevant reading in the Carey textbook and come to class prepared to apply what you've learned.